Okay, let's do this. So we actually kind of already did our intro to this chapter, chapter 13 on equilibrium. All right, so let's just kind of remind ourselves real quick. We said that we were going to take this very simple reaction where A is converted into B, and we're going to make one of these plots just like we did in our kinetics chapter, where we're going to plot the concentration change over time. We start our reaction with only A in our flask and none of that product B. And then as this reaction progresses, the concentration of reactant decreases and the concentration of product increases. And this is going to occur until they reach this point in time where the concentration of both reactant and product are no longer changing anymore. All right, and this region right here is what we call the equilibrium of this reaction. All right, importantly, all reactions, they proceed towards their equilibrium. And at equilibrium, as this graph illustrates, the concentrations of reactants and products are constant. They're no longer changing. All right, and that what we sort of said is we had to update our way of looking at chemical reactions. We're not going to sort of look at them as if we were in Chem 1A anymore, where we only think about reactant getting converted to product, but we're also going to consider the reverse reaction that happens as well, where product gets converted back into reactant. Both of these reactions are occurring at the same time, going back and forth, and this will happen until they reach this region of equilibrium, where the rate of that forward reaction is equal to the rate of the reverse reaction. All right? And this was kind of where we stopped because we needed that little bit at the bottom there for our kinetics chapters talking about rates. We're going to pick up from here. All right, cool. So again, talking about reaction equilibrium, we're going to introduce this very important concept, the equilibrium constant. All right, we always use an uppercase K for our equilibrium constants. All right, so all chemical reactions have a characteristic equilibrium constant value. All right, so what do I mean by that? Well, just like we know, like all of our metals have different densities, right? And we can go to some book somewhere and we can look it up, and that's a characteristic of that particular metal, that density value, right? Just like that, every chemical reaction, we can go look up in a table somewhere what its equilibrium constant is, what some value associated with that reaction is. All right, and so what this tells us, what our equilibrium constant will tell us, is which direction in our chemical equation by that, by direction in our chemical reaction, I mean reactants or products. All right, which side is favored at equilibrium? All right, so again, every chemical reaction that we want to study, we can go to some book somewhere and look up its equilibrium constant, and that will tell us for that particular reaction which side of our chemical equation, reactants or products, which one is going to be favored at equilibrium. All right, our equilibrium, we'll sort of get a little bit more fancy than this, but for right now, our equilibrium constant is the product concentration of products over the concentration of reactants. All right, products over reactants. That's what we're going to chant to ourselves every time we build an equilibrium constant here. All right, so let's think about this. If K is greater than 1, is that a reaction that's going to favor our products or our reactants? Let's look carefully at our expression for K here. If this value of K is greater than 1, what has to be bigger, the numerator or the denominator? The numerator, right? So if K is going to be greater than 1, that means I have to have more products at equilibrium. So this would be an example of something that favors our products. All right, and we're going to go a little bit more than that. We're going to give it these sort of cutoffs here. All right, our upper cutoff is 10 to the positive 3. Okay, if K is between 1 and 10 to the positive 3, that is a reaction that favors our products, but we would say it only weakly favors our products. Whereas if K is a super huge number, something greater than that 10 to the 3 cutoff, we would say that this is a reaction that strongly favors our products. All right, and then what if our value of K that we look up is actually less than 1? All right, again, let's go to our simple equation here. Products over reactants. If this is going to be less than 1, what's going to be bigger, the numerator or the denominator? The denominator. So this would be a reaction that favors the reactants. All right, but again, we're going to have this sort of cutoff. Now it's not going to be 10 to the positive 3, but 10 to the negative 3. If your equilibrium constant is in this range, we would say it weakly favors the reactants. And if K is even smaller than that, smaller than 10 to the negative 3, this is a reaction that strongly favors your products. Strongly favors reactants, sorry. What's up?
If a reaction favors the reactants at equilibrium, doesn't that make it a product and not a reactant?
So what it all is going to be dependent on how you wrote it here, right? Okay. So if we wrote this reaction and our K is less than 1, that means it favors the reactants, which also just means you're going to mix things together and absolutely nothing's going to happen, right? No chemical reaction is going to occur because that equilibrium is going to favor this side of that chemical equation.
So we just assign them arbitrarily, which one is
Totally.
reactant and
Yep.
product. Okay.
Yeah, every reaction is reversible. You can pick it up and flip it upside down and look at it that way as well, and it's just going to change the verbiage. Okay, cool. So if we had a reaction that strongly favors our products, that is a reaction that we can think of as going to like 100% completion, and we can write that with that just single reaction arrow. That's a good way to describe that reaction, right? Reactants getting converted to products. Anything in this range right here, we call this our dynamic equilibrium range. All right, and this like dynamic equilibrium, we'll talk a little bit more about why it has that word dynamic in front of it. All right, but this means you have an appreciable amount of both reactant and product at equilibrium. All right, so in this dynamic equilibrium range, this is when we want to use those two arrows to remind ourselves that this reaction is really going in both directions at the same time. All right, I'm pretty sure this is technically correct, although sometimes, I'm not going to lie, I get lazy and I just do the one that has the two heads on it. I don't really care, but I'm pretty sure this one's technically correct. So let's just note that. Anyways, and then if we do one that strongly favors the reactants, you'll kind of see that one of two ways. Either A being converted to B doesn't really happen, right? So there might be a little X saying, nope, that reaction's not going to really occur. Or we could just draw our arrow in the other direction. These are both sort of saying the same thing, which is that reaction does not really favor that product side at all. Okay, cool. So we said that K is products over reactants, and that is true, all right? But let's build one of these for a real reaction, what we would call our equilibrium expressions. Okay, so I'm going to leave a space up here for some rules. We're going to have just 3 simple rules on how to build these, but then let's look at a balanced chemical equation that we're going to do as an example here. Okay, so we're going to take nitrogen gas and fluorine. All right, these are going to combine. Since we're talking about equilibrium, we'll be good and use our double-headed arrow here to make nitrogen fluoride, nitrogen trifluoride rather. All right, so everybody take a second to balance this for me. All right, so we're going to build this expression here. So let's put down our K equals, all right, and our first rule, again, is products over reactants. All right, we're going to chant that to ourselves 1,000 times this semester. All right, whenever we build these equilibrium constants, we're going to put our concentration of our products over our concentration of reactants. All right, now since I have these 2 reactants here, I'm going to be multiplying their concentrations in my equilibrium expression. All right, so products over reactants. Okay, cool. The next thing is these stoichiometric coefficients are also going to appear in our equilibrium expression. Our coefficients become exponents. All right, so what do I mean by that? Well, let's look here. We have this 2 out front of my product, that NF3, that nitrogen trifluoride. That means I'm going to raise that concentration of nitrogen trifluoride to the power of 2. My coefficient of 2 became an exponent of 2. All right, what other exponent do I need to include here? The 3 from my fluorine. I'm going to need to cube that fluorine concentration. Cool. All right, so This is what we would call a Kc, because my amounts here are given in concentration. All right? And what we can, if we plugged in our equilibrium values, we get our equilibrium constant. Again, that constant value for this chemical reaction, we could have gone and looked it up in a book somewhere. And this is kind of the magical thing about equilibrium, is it doesn't matter like how much of each reactant or product you start out with. You mix them together, this reaction is always going to come to equilibrium. And if you put those equilibrium concentrations into this expression here, you'll always get the same value, right? You could have started with 1 mole, you could have started with 1,000,000 moles. You're going to get the same value once this thing comes to equilibrium if you plug them into this expression here. All right, this is a Kc because it's done in units of concentration. Importantly, for gaseous reactions, we can also define what's called a Kp. And what do we think the P stands for? Pressure. All right, it turns out, and you can use the ideal gas law to convince yourself that concentration in molarity, moles per liter, is actually directly proportional to pressure. And in some experimental setups, it might be easier to measure pressure than concentration. So this would just be the pressure of that, nitrogen trifluoride divided by the pressure, so products over reactants. And again, those coefficients are going to become exponents. All right, so let's just use this Kp real quick, this equilibrium expression here. All right, if the partial pressure at equilibrium of, let's do that, product NH3 equals 2.45 atm. The partial pressure of nitrogen is 0.65 atm. And the partial pressure of that fluorine, did it again, equals 0.17 atm. Calculate that equilibrium constant for me. All right, so I'm going to plug in my constant or my pressure of my product. That was that there. Pressure of my nitrogen. And finally, the pressure of hydrogen. Just plug in those values for my problem. All right, I'm going to be good and put in my units so I can make a point here. Punch this into my calculator. The value of Kp is 1879.6. We're just going to keep it there. All right. We are officially kind of going to be in that portion of our course where we're going to kind of conveniently ignore sig figs for this for right now. All right. Cool. But I do want to look at my units here. So I have ATM squared over ATM times ATM cubed. All right, what's that going to end up simplifying to? So, yeah, so I'm going to get rid of both of these on top and 1, but that's going to take me to 1 over ATM squared. Okay? Your units are going to completely depend on that chemical reaction. They are not consistent for every equilibrium constant. It depends on your balanced chemical equation. So you're going to have to look at your equilibrium expression to get your units. Okay? But lastly, what can we say about the value of this equilibrium constant? Would this strongly favor the reactants or products or what? Weakly? What's going on? So this is actually, it's barely over that cutoff, right? So it's pretty squishy on the line here, but it is technically over that 10 to the 3. So this one we would say would strongly favor. And it's greater than 1, so strongly favor that products. Okay, cool. Let's do another example. Let's build another one here. We're going to look at now a precipitation reaction. This one really is pretty strongly favors the product, so I'm just going to put that arrow in there, but nonetheless. All right, so here's our balanced chemical equation. You're going to, our unbalanced chemical equation rather, you're going to balance it. Can we do a Kp for this reaction? No, it wouldn't make any sense. So we're just going to have to do a Kc. So once you balance this chemical equation, you're going to give me your Kc expression for this reaction. All right, so I'm going to do my products over reactants, my barium phosphate times my sodium chloride divided by my reactants, my barium chloride, and my sodium phosphate. All right, and then I need to turn my coefficients into exponents. So I'm going to raise the power of that sodium chloride to 6, barium chloride to 3, and sodium phosphate squared. All right, cool. So if this is what you got, that's awesome. That's where we've sort of gotten to this point, but this isn't quite right here. All right, there's one more little rule we have to add to building our equilibrium expressions, okay? And the problem is this term right here, this concentration of barium phosphate. Barium phosphate is a solid, right? In order to be a solution and have a concentration, by definition, that solute has to be homogeneously distributed throughout that solution. That's not going to be the case here. As soon as that barium phosphate forms, it's going to settle to the bottom. Talking about its concentration doesn't really make sense, and in particular what we're going to do is we're just going to exclude these from our equilibrium expressions. Turns out that these are independent of the amount of solid as well as pure liquid that is formed in a chemical reaction. All right, so my actual equilibrium expression here will just be this exact same thing with that one term excluded. All right, so the last little rule that we're going to add, products over reactants, coefficients become exponents, and we're going to exclude solids and liquids, which implies that only gases and aqueous will appear in your equilibrium expression. What's up?
Why is that the case? Because I know that when we do net ionic equations, it's the same thing. And I'm just curious as to why.
Well, so net ionic equations, you don't exclude the solid, you just don't break it up into its two ions, right? So you still whatever. But it's in order for a reaction to occur, there has to be these collisions between reactants, right? Well, this solid that settles in the bottom isn't going to be colliding around with everything else, so it just doesn't really contribute to the equilibrium of those reactions. So it turns out that in a precipitation reaction, for example, that equilibrium is independent of the amount of solid that's formed. You could start out with a whole bunch of solid already in the bottom and you'd still get a bunch of reaction.
Thank you.
Yep. All right, so, okay, here we were, sorry. Our equilibrium expression, again, products over react. This is a good example of all the different things that we learned to build into our equilibrium expression. We have our products over our reactants. We have our coefficients that have become exponents. And we've excluded any solid or liquid, pure liquid from that equilibrium expression. Okay, cool. All right, so we are going to, and I guess just to take a step back, we did talk about one type of problem that we could do. That wasn't you. Wherever that was, there we go. One problem that we could do is if you're given these values at equilibrium, you can turn around and plug them in to your equilibrium expression in order to get your equilibrium constant. Okay? So, simple enough. If I say, hey, here's everything at equilibrium, you plug it in, you get your equilibrium constant, okay? Don't worry, it's not that easy. So, what we're going to do is we're going to learn kind of a new problem-solving strategy that's going to be specific to these equilibrium problems, and it's something that we're going to use kind of over and over again. Use over and over again. So for example, next chapter we study acids and bases. We talk about the equilibrium of acid-base reactions. So we're going to sort of use this same format over and over and over again, and these are what are called ice tables. I see we have some ice table fans out there. They're not bad at all.
I love the ice tables.
Yeah, they're fine.
I thought they were fun.
Okay, we are going to need like a sample equation to our chemical equation to use here. So we're going to take oxygen reacting with fluorine. All right, we're going to study this equilibrium here as it gets converted to oxygen difluoride. All right, so let's balance this chemical equation. And since we're talking about equilibrium here, we're going to need an equilibrium expression. Since these are all gases, let's just get some practice building that Kp expression. All right, so we have our products over reactants, and we've raised the power of each of those pressures based on these coefficients here. They were all gases, so we didn't have to exclude anything from our equilibrium expression. All right, so we're going to kick off this reaction. This is the reaction that we're trying to study here. All right, so what we're going to do is we're going to take some oxygen and some fluorine, and we're going to mix them together in a flask. All right, so let's say that we're going to take 3.1 atm of fluorine and 1.6 atm of oxygen are combined into our flask. Okay, when the reaction reaches equilibrium, the partial pressure of oxygen is 0.3 atm. All right, so we're given some initial conditions here, and then we're told at equilibrium what the pressure of oxygen is. And what we want to know is what is the partial pressure of our product at equilibrium. But also, what is the value of that equilibrium constant? All right, so I'll give you all a second to copy this problem down, and then let's talk strategy here. All right, so first of all, if I want to calculate my Kp here, I need the pressures of each of these gases. But again, it's really important that when we're looking at these expressions, we realize that this is only going to work. It's only going to give us our equilibrium constant if we plug in these values at equilibrium. Can't just willy-nilly be plugging in numbers to the equilibrium expression and get your equilibrium constant. They have to be the values at equilibrium, the partial pressures at equilibrium. I got one of those from my problem. Which one? I know this one. Cool. I'm missing literally everything else, right? That's the problem. Okay, cool. So this is what we're going to need our ice tables for. All right, so let's talk about how we build our ice tables. So as the name implies, this is going to be a table. All right, our columns are the amount of our reactants and products. In this case, we're talking about pressure, partial pressure, so our amounts will be in pressure. If we were talking about Kc, they would be in concentration or molarity. And the rows on our table are going to be I, C, and E, hence the name. All right, so let's do it. We're going to make a table. Okay, we're going to have these three columns for our two reactants and one product, right? And since we're talking about pressure, we're going to head them with the pressure. Pressure O2, pressure F2, and then our product, OF2. I'm going to put my units up at the top here so I don't have to keep track of them throughout. These are all in units of ATM. All right, and again, we got these three rows, I, C, and E. So far, so good? All right, cool. So what does the I stand for here? So the I is our initial. All right, in this box, we're going to put the initial amount of our reactants and products. Okay, so again, back to our table. I stands for initial. Help me fill in this table here. Who's got one thing?
Oh, sorry, the numbers.
Yeah, so just our initial amounts of each one. Do we have an initial amount of O2 in our problem here?
1.6.
All right, so we got 1.6 ATM of that O2. Do we have initial amount of fluorine? That's our 3.1. And what about the initial amount of product? Is there any in there?
I guess 0.
Yes, so we don't have any that's been added to that flask, so Before any reaction has occurred, the amount would be 0. All right, so the next box, the C. C stands for change. This is a change in the amount of reactants and products as they react to reach equilibrium. Right? Kind of the whole shtick of this reaction is that it's going to occur until it reaches equilibrium. This change box is where we're going to account for how much reaction has occurred. And importantly, this is what we do not know. All right? This is what we're going to try to have to figure out here. So what we're going to do is we're going to leave it as a variable, or rather we're going to use this variable. Okay, so I go back to my change box here, and across the board, I'm going to put in that variable x. Boom, boom, boom. I don't know how much of this reaction occurs. That's what we're trying to solve for and figure out. All right, but we're not quite done yet. Okay, we got to think about the relative sign of these change boxes here, because our reactants, as this reaction occurs, are going to decrease in concentration. But what's going to happen to my products? It's going to increase. So my change is going to be different, specifically the sign of change. My reactants are going to decrease, so I need a negative sign in my change box for my reactants. And I could just leave it alone or put a positive sign in there for the change box of my products, because products are going to increase. Okay? And then one last thing to consider. According to my balanced chemical equation, for every 1 molecule of oxygen that reacts, 2 molecules of fluorine are reacting. Right? So there's going to be twice as much fluorine consumed as oxygen. So our stoichiometric coefficients are also going to appear in our ice table here. Right? Both my fluorine and my oxygen difluoride have this coefficient of 2 in my balanced chemical equation. That coefficient is going to appear in that change box as well. Okay? So again, the C stands for change. We're going to use this variable x. All right, we got to pay attention to the sign of x. It's going to be negative for reactants and positive for products. And then we're going to include those stoichiometric coefficients. Cool. All right, so then the last box, the E, stands for, you guessed it, equilibrium. All right, but we are going to have a very specific strategy for how we fill in these boxes here. Okay, your equilibrium box you're going to fill in by summing the I and the C box together. All right, this is the amount of reactant and product at equilibrium. Okay, but when we fill out our ice table, we're going to fill in that row by summing those previous 2 rows together. All right, so now let's do this first column together. I'm going to sum these two boxes together. So that means it's going to become 1.6 minus x in my equilibrium box here. All right, take a second and fill in the rest of it. Okay, 3.1 minus 2x. And 0 plus 2x is just 2x. Okay? All right. So, importantly, if we look at our equilibrium expression here, we said that these variables in my equilibrium expression had to correspond to these partial pressures at equilibrium, right? So the partial pressure of OF2, my product at equilibrium. And importantly, that corresponds to a specific box on my ice table now. All right? Corresponds to the partial pressure of OF2 at equilibrium. So that is this box right here in my equilibrium expression. Right? Likewise, my PO2 at equilibrium would be this 1.6 minus x. And my PF2 at equilibrium, the 3.1 minus 2x, right? Those are what those boxes represent, the amount of each of those at equilibrium. Okay? Now, this is always going to be our strategy for building our ice table. Okay? And our ice table contains this unknown variable that we don't know, x, and we're always going to be trying to solve for x. Exactly how we solve for x is going to depend on the information that's given to us in the problem. All right, so let's read our problem carefully. Which one of these boxes, orange, green, or red, do we know about from our problem? If we read our problem, it says that when the reaction reaches equilibrium, so it's at equilibrium, the partial pressure of O2 is 0.3. So I know that 1.6 minus x has to equal 0.3, so that's how we're going to solve for x here. Okay, I have my pressure of O2 at equilibrium from my problem. That's that 0.3 atm. Well, this has to be equal to the pressure of O2 at equilibrium from my ice table, which is that 1.6 minus x. All right, so everybody take a second, get me the value of x here. We can be good. Our units here were atm. All right, so we rearrange and solve for x. We'll get 1.3 atm. All right, cool. So we're done. No, all right, look, so this is kind of going to be how these problems work. You're going to spend all this time building your ice table. You're going to start doing a bunch of algebra to solve for x, and you're going to get x and be like, okay, great, done. Let's move on with our lives. You always want to go back and reread the problem carefully, okay? Our problem, the first one, is asking us, what is the partial pressure of OF2 at equilibrium? Is the partial pressure of OF2 at equilibrium x? No, according to my ice table, what is the partial pressure of OF2 at equilibrium? 2x, 0 plus 2x, sure, yeah. Okay, so we're going to go back and double check our ice table to make sure our partial pressure of that product is not just x, but 2x. Or 2.6 atm. Okay, so then the last question I want you all to try to answer on your own here after what we've discussed about these ice tables. What I want to know now is what the value of this equilibrium constant is. So you need to plug in equilibrium pressures to our Kp expression here. All right, so all I did was go through, plug in x for each one of those equilibrium boxes to get that value, and then turn around and plug that into my equilibrium expression here. Okay, I get an equilibrium constant. We're just going to pick 3 sig figs of 90.1. What should my units be? So ATM squared divided by ATM times ATM squared. I'll be left with inverse ATMs. 1 over ATM. Cool, and then lastly, what can I ask you about this reaction in terms of what it favors? So this one would weakly favor the products. It's greater than 1, but less than that 10 to the 3, less than that 1,000 cutoff. So this we would say weakly favors the products. All right, cool. So we have this new strategy that we're going to use for solving these equilibrium problems called the ICE table. We have columns for each of our reactants and products, and then the rows are I, C, and E. I stands for the initial concentration of each, or pressure in this case, from our problem. The change box we're going to leave as a variable. So we got a variable in all those change boxes. We also got to worry about the sign of that change box, as well as make sure to include our stoichiometric coefficients. And then in order to get the equilibrium box, we sum up those first 2 rows. Okay? For this particular problem, our way of solving for x was we were given one of these boxes in our problem. We were given the equilibrium pressure of one of these components. And so we got x, and then we were able to find our other stuff like the pressure of our product at equilibrium, and finally the Kp of our reaction. Cool. All right, y'all are going to do one more for me here on your own, and then we'll go through it together here. But let's see how much we can do. Okay, so another precipitation reaction, but this time with sodium hydroxide and iron 3 chloride. Okay, so we're going to combine 2.3 molar NaOH and 1.5 molar iron 3 chloride. Okay, and at equilibrium, the concentration of sodium chloride is equal to 2.28 molar. I want you all to find me that Kc value. All right, and so a good place to start, you're going to start by building that Kc expression. And then finally, you'll need an ice table to fill it all in. All right, so let's do this. So I built my, well, I guess first I balanced my chemical equation, and then I built my equilibrium expression here by putting products over reactants, but omitting that iron 3 hydroxide because it's a solid. Products over reactants, my coefficients are exponents. All right, so here's my Kc expression. And then I set up my ice table now with concentrations of my reactants and my product. I actually omitted that solid product since it's not going to plug into this expression at all. Don't really have to keep track of it. And I have my initial amounts of everything that are in this flask before any reaction has taken place. So now I need to do my change boxes. Again, we're going to leave these as variables. All right. What should the sign be in the change box for sodium hydroxide? Negative. Reactants get consumed. Same thing with iron 3 chloride. But my sodium chloride product needs to be positive. All right. And then I also need to include those stoichiometric coefficients. Right. So sodium hydroxide had a 3. Iron chloride just had a 1. And sodium chloride had a 3. So those are going to appear down here as well. If it's a 1, we don't have to bother writing it. Okay, so then we're going to sum up for our equilibrium box. We're going to sum up those first two rows. So we get 2.3 minus 3x rather. 1.5 minus x and 3x. Okay. And once we get x, we can turn around and plug that all back into our problem here, because again, that's what these equilibrium boxes correspond to, is these concentrations at equilibrium. Okay. In this case, I can solve for x because I know the value of one of those boxes. Which one of those boxes do I know? Green, red, or orange? The orange one. So this problem tells me that at equilibrium, the concentration of that product is that 2.28. Okay. So my concentration of NaCl at equilibrium from the problem, that 2.28. I know that has to equal the concentration of NaCl at equilibrium from my ice table, which is 3x. Okay, so that means x is equal to 0.76, in this case molar. And I'm done. No. So what do we got to do? We got to go back and plug these values into our ice table here. Now that we have x, we're going to have to solve for x in each one of these equilibrium boxes. Move this down here. All right. Sorry. Okay. All right. So 2.23 minus 3x is 0.02. All right. 1.5 minus that x gives me 0.74. And then 3x is that 2.28. So I'm going to turn around and plug these values into that equilibrium expression, since now these are my amounts at equilibrium. So 2.28 cubed over 0.02 cubed times 0.74. and I get 2.00. Again, we're just going to keep 3 sig figs times 10 to the 6. All right, and my units here would be inverse molar. Okay, so what can we say about this chemical reaction in terms of what it favors based on the value of that equilibrium constant? Favors the products strongly or weakly? Strongly favors the products. All right. So if we have our initial conditions and we know the concentration of one of our products at equilibrium, or one of our products or reactants at equilibrium, we can use this ice table method here to plug in those equilibrium values and get the value of our rate constant. Okay? We will be playing this game in lab next week with an experiment that we'll be doing. We're going to measure concentrations, how they change, and plugging them into our equilibrium expression to figure out the equilibrium constant for that reaction. All right? We're going to continue with this ice table business next class as well. We got a few different variations that we can do here, throw at you, but that's good for right now, so we're going to leave it there.